All right, we're gonna not cover a whole lot of new material before the midterm. The midterm is going to be on Thursday of next week. We're going to do just a little bit of material today. Then we'll do review on Tuesday for the midterm, and then the midterm on Thursday. We're going to look at the different functions for two binary variables. So if you have two binary variables, x and y, that one's not working. We'll go with blue. X and y. Okay. You can have, when you have so many binary variables, you can have 2 to the 2n functions with those variables. So in this case, we'll have 16. So there's 16 possible functions that you can have with two variables. 2 to the 2n, so that's 2 to the 2 times 2, or 2 to the 4th, which is 16 functions that you can have with two variables. Those functions have truth table, state tables like so. Some of these functions you'll recognize. So these are the functions and the outputs for each of those functions. Now, some of them you may not seem like they're really all that functiony. Like F0 is just null. F1 is and. Might recognize that one. It is x and y. F2. This F2 here is a function called inhibition. It's x, but not y. So F2 inhibition x, but not y. It is also written as x/y. They don't see that very often. F3 is just a transfer. It's just x. It just matches what is in the x column. Doesn't matter what y is. F4 is another inhibition, but it's y, but not x. Not x, y, or y/x. The F5 matches the y column, so this is another transfer. And it's just y. It doesn't matter what x is. It just matches the y input. Let's see here. F6 might recognize as exclusive OR. X, y, exclusive OR y. So it is a familiar function. Another familiar function, F7, is OR, which is x plus y. Seen that before. F8 is NOR. Which is, there is a symbol for that. It's an arrow pointing down. So it would be X, arrow down, Y. Equivalence, when the two input variables are the same, it's called equivalence. That's F9. It's also the exclusive NOR, but and it doesn't have a symbol, so you do the X, Y prime, X exclusive or Y, and then prime it all. F10 is just the complement. It's the complement of Y. So it's just y prime. F11, implication. It has a symbol. It's y or not, or x or not y. So F11 is implication. X or y prime, and that is this, uses the symbol x, and you might see recognize that symbol as being a subset symbol from a math class, but in engineering we use that for implication. If y, then x. So if x, then let's say that's F11. Yeah, if y is true, then x is true. Or if y is false, then or x is true, then it's true. Let's see here, F12, another complement. F12. And that's x prime. It's the inverse of the x column. Another implication, it looks like, in F13, not x or y. Not x or y. And that's x, no, it's y, x, with that implication symbol. If x, then y. And 14, might recognize this as the NAND, and that has the symbol of x up arrow y. So that's the NAND function. And finally, the last function, F15, is identity. It's just one. So this is 0 for null and 1 for the identity. So 16 possible functions with 2 variables. Null, you would just connect it to ground. Identity, connect it to power. The transfer, F3 and F5, you just have a wire connecting Y to the output, or X or Y to the output. Where is it? Oh, the inverse, their complements, have the Y or X running through an inverter, and that's all there is to it. So 6 of the functions, let's see here, 2 functions don't require anything, are just the null and identity. And 4 functions are with unary operations, complement or transfer. And then 10 functions with binary operators that define 8 different operations: and, or, NAND, NOR, exclusive OR, equivalence, inhibition, and implication. So only 10 functions use both inputs. The other 6 use only one input or no input at all. So that's everything you could possibly do with 2 input variables. Now, if you had 3, it would be 2 to the 6th power, which is what is that? 64 or 32? 64 different functions with 3 variables. A little bit much to do on a whiteboard, but that is what you can do with all the inputs. Let's see here. Went through that faster than I was expecting. The only functions that are implemented in chips typically are the AND, exclusive OR, NOR, complement, and NAND. Those are the only 6 that are typically implemented, because the inputs are interchangeable on those. So it doesn't matter if it's Y and X or X and Y. It doesn't matter. It's symmetrical. You can implement that easily on a chip. Whereas X, Y prime is not symmetrical. You switch the switch the inputs around, and you get F4 instead of F2. Again, transfer and null and identity do not require a chip. Equivalence could be implemented on a chip, but I don't believe anybody manufactures a chip with just 4 exclusive NOR gates on it. It's not in the 7400 family of chips, like what you use in Digital Logic Lab. Yes? I'm sorry? This is all the functions with 2 input variables. Yeah. I'm sorry? Oh, that's the state tables for each of the functions. Am I not getting the question? Right. Yeah, the different functions of 2 binary inputs. So 2 to the 2n functions with n inputs. So, yeah, that's the 6 that I have circled are the only ones that are actually implemented in chips because they are symmetrical. They do not. Oh, I forgot one. Yeah. Or yeah. So well, complement is on there twice, so it's still only 6 functions. Complement being on there twice. One thing that I'm not going to go into in great detail, just let you know that it's out there, and you might run into it. Everybody got this, or I'm sorry? Still copying it? Okay. Positive and negative logic. Let's see here. What is a considered a 1 and a 0? This is all positive logic, assumed to be positive logic, where a high means a high level means 1, and a low level means 0. Occasionally, you have what's called active low, which is the opposite. A high means a 1, or a high means a 0, and a low means a 1. I'll just, okay. But let's get this out of here. So, you have 2 different types of logic: positive logic and negative logic. Positive logic, 0 is low, 1 is high. Negative logic, 0 is high, 1 is low. Well, you'll see this in most of the time is enable bits and well, in enable bits and in multiplexers or decoders, I should say. So negative logic, you'll see something like this, like an enable with a bar over it. That means enable is on when low, off when high. So when you have that sort of situation, you just got to remember that the bar means it's inverted. So, like, I forget, did we cover tri-state buffers yet? Not yet. Okay. Good time to do it. A tri-state buffer. No, it's not an inverter. This is a tri-state buffer. When the enable, well, let's have the state table. When the enable is, and you'll see a bubble on the input rather than on the output, indicates that it is active low. As opposed to active high. So when the 0, 1, and the enable is low, the output is A. When enable is low, the output is A. Okay? And this is why these are called state diagrams rather than truth tables. Although people use the term interchangeably, they do mean different things. When the when the enable is high, the output is a high impedance state. What that basically means is, say this is a battery. All the gates that we've been looking at so far, you have high over here, low over here. What's the third possible condition? No condition, no connection at all. Neither high nor low. It's like the wire isn't connected to the battery at all. So that is the high impedance state. And you will, for you computer engineering and electrical engineering students, will learn what impedance means in electronics 1 or 2. I don't remember. But it's a disconnected state. So it will not read high or low. And that third state is why it's called a state table as opposed to a truth table. A truth table only has true and false. Truth tables are used in philosophy and math classes, not in engineering classes. So the enable, when low, will allow the signal to traverse from the input to the output. When it's high, it will disconnect it. It doesn't matter. X means don't care. It doesn't matter what A is. It'll be in a high impedance state. Because of that, with the let's go ahead and erase this. You can have two. In this situation, oops, I keep doing that. It's not an inverter. Now, at the beginning of the semester, I told you that you don't connect the outputs of gates because you can cause a short circuit. That would be a bad thing. But in this case, you have a situation where one of the two buffers is in a tri-stated condition, a high impedance state, and therefore the other signal can travel to the output just fine. So the state table for this would be, you have select A, B, out. Select is high, then select is high, and select is high. That would make the A active, so 0, 1, 0, 1, and it doesn't matter what B is. And if it's low, A would be in a high impedance state, and B would be active, so it doesn't matter what A is. So you'd have what is called a data selector. One of two. This is also called a multiplexer. Or MUX. And in this situation, you can see where the negative logic comes into play and how to handle it. So here you have a bubble here on the output of this inverter and a bubble on the input of the tri-state buffer. They cancel each other out. So when this is high, this is active, because it high to low, and then the two negatives cancel each other out, the two inverters. Whereas for B, it just has the one inverter on the input of the enable bit or enable pin of the tri-state buffer, and so it is active when the input, the select input, is low. But yeah, and you can string together multiple out inputs and have more select lines, and you can expand that out to more to 1 of 4, 1 of 8, 1 of 16 multiplexers. Although I don't think I've seen 1 of 16 before. Most commonly see 1 of 2, 1 of 4, and 1 of 8. But yeah, I think that will be about it for the day.